Hello, my name is Angarita. I'm a PhD student at the University of Alaska Fairbanks, and I would like to talk to you about a new method that we have developed to quantify morphology changes using radar images. So why do we want to quantify morphology changes? Well, doing this will help us to identify future hazards, like the direction that a possible pyroclastic flow might take. So people have done this using photogrammetry techniques and optical images, as we can see here for the Stromboli volcano, where using those optical images, they were able to infer changes in the topography. So how about if we do this for some of the eruptions that we had here in Alaska? For instance, we can see here the eruption for Shishaldin Volcano between 2019 and 2020. However, if optical images cannot penetrate to clouds and they do not work during nighttime. And in Alaska, we have this issue. However, radar images are less susceptible to these issues, as we can see here for a set of TerraSAR-X images that span the 2019-2020 Shishaldin eruption. You can see in the upper map, Shishaldin Volcano, and is located in the Aleutian Islands. So the main question is, how can we use these radar images to quantify morphology changes? So as you can see here, we can see some topographic features. So it will be ideal if we can relate this image to a digital elevation model. However, digital elevation models come in geographic coordinates and radar images come in radar coordinates. So the first step is to change our digital elevation map into radar coordinates so we can be in the same coordinate system. When we do this, we can see some elevation features in the radar image. This becomes clearer if we take the gradient with respect to the range coordinates. But why does this happen? Well, in theory, an amplitude image is a linear function of the gradient of elevation. Or in other words, we can have a gradient of elevation per each amplitude image. And then with that gradient of elevation, we can integrate it and solve for the integration constants to have an elevation map per each amplitude image. We can condense all this process into one matrix that will allow us to go directly from an amplitude image to an elevation map using an appropriate DEM. So now the question is how well our method works. So for this, we have simulated a collapse in Shishaldin crater. As you can see here, the collapse has a maximum magnitude of 10 meters. And the main question is if our method will be able to capture this synthetic collapse. So we follow the next process. First of all, we reconstructed a DEM from the amplitude image. Then we subtracted our synthetic collapse from that DEM. Then we reconstructed an amplitude image simulating a possible shadow that the radar signal will have. Then we reconstructed the DEM from that synthetic amplitude image. And then subtracting the original DEM, we are able to see that our method was able to detect that synthetic collapse. So now we have to validate our method to previous studies, and Mount Cleveland is a perfect place to do this, as two studies were performed here. The first study was performed by Wang and others in 2015, where they used radar images to track changes in elevation due to a dome growth and also changes in the area for that dome. The second study was performed by Werner and others in 2017, and this was done using thermal data. So in Mount Cleveland, they were able to track dome growth in 2011 using two different data sets, one composed by radar images and the other one composed by thermal data. So if our method works, we should be able to get similar results. The plots in both cases show the increase in elevation through time. So here we have the amplitude images that span this dome growth between 2011 and 2012. And here we can see the corresponding elevation map for each amplitude image. When we look at a point inside the crater, we can see the changes in elevation for that dome growth. And you can see also the results from the previous studies. Our results are represented by the red points, and the rest of the results are represented by the black points and the lines. So as you can see here, the results from the study from one and others fall inside our confidence of interval, and our results fall inside the confidence of interval from the study of Werner and others in 2017. We can see also that the increases in elevation are significant if we compare it to a point far away from the crater where the changes in elevation are insignificant. Okay, now that we know that our method works, how about if we use it in Shishaldin Volcano for the 2019-2020 eruption? In the video, you can see Shishaldin crater in 2021 when the volcanic activity decreased a lot. So again, we have here our amplitude images, and here we can see the corresponding change in elevation map. When we look at a point inside the crater, we can see the growth of a scoria cone up to 30 meters, and then its posterior destruction after a major explosion in January 7, 2020. Then we can see a slight increase in elevation after the appearance of a new vent in March 2020, and then a period of stability and then some collapses when the volcanic activity decreased. As in Cleveland case, when we compare the point inside the crater to a point far away from it, we can see that the changes in elevation are significant. The results that I show you comes just from the descending direction of the satellite, but we also can use the ascending direction, and we can merge the two time series as the reference images are close in time. And we can see that we see similar trends in both directions. Also, when we georeference our results, we can see some decrease in elevation due to ice melting where the lava flows past. So all the code that was used to for Shishaldin Volcano and for Cleveland is publicly available through Zenodo. So I invite you to look at it. And also, if you want to look for more information, I invite you to read our recently published paper at JGR Solitaire. Thank you so much.